Good morning. Today what we are going to do in Unit 5 of Calculus 30 is take a look at one more topic that would give us a complete picture of graphing different kinds of functions. We've looked at lots of things with the first derivative, the second derivative, increasing, decreasing, concavity, inflection points, all sorts of things. But asymptotes are also a significant feature in a graph, and so we need to take a look at how we can algebraically determine vertical asymptotes and horizontal asymptotes. I'm going to start with the easier of the two, the vertical asymptotes, because that is something that we've already looked at in the past, and so this is a bit of a refresher. The horizontal asymptotes are ones that are a little bit newer, and so we need to take a look at those in more detail. Okay, starting with vertical asymptotes. What we learned in Pre-Calc 30 was basically that vertical asymptotes occur where an x value is going to cause the denominator of a function to be 0. That situation where we have a number over 0 where that function is undefined. A more advanced definition, I guess you could say, is when you take a look at the limit as you come into a value from the left side. If it approaches positive or negative infinity on either side of that x value, on the left side or the right side, what we have is a vertical asymptote at x is equal to c, whatever value we're approaching. And so while the limit process is 100% correct, I think most people will fall back to where the denominator is 0. That's something that's more familiar, a little bit more straightforward. In some cases, not always, so that's why we have a couple of options. In these three examples, real quick, when you take a look at the fact that in this first function, we have a denominator of x, and so if we do not want our denominator to equal 0, that means x cannot equal 0. That is where we have a vertical asymptote. Second example, denominator is x minus 3. We do not want our denominator to equal 0. Treat it like a little equation. If you need to, move over the 3 so that you can see that x cannot equal positive 3, and that is where we are going to have our vertical asymptote at x is equal to 3. And I guess maybe I should say this more clearly. So that means that we would have a vertical asymptote at x is equal to 0. We would have a vertical asymptote at x is equal to 3. So when we talk about the denominator not equaling 0, this is talking about that non-permissible value. We have that non-permissible value. X cannot be 3, and what that corresponds to in the graph is that we have a vertical asymptote at x is equal to 3. So in a case like this, where we have a function with a denominator like x squared plus x minus 2, it's a little bit more work in order for us to get to what our non-permissible values are so that we can see where our vertical asymptotes are. All it means is that we need to take a second to factor this. When it's factored, the denominator is a nice trinomial, two numbers that multiply to negative 2 that add up to positive 1. We'd have x plus 2 and x minus 1. So in terms of non-permissible values, factors that make the denominator 0, we do not want the denominator to be 0. The factor x plus 2 means that x cannot be negative 2. The factor x minus 1 cannot equal 0. So that means x cannot equal 1. So that means that we have a vertical asymptote at x is equal to negative 2 and at x is equal to positive 1. Now there's a slight difference in terms of what I've written here in terms of the non-permissible values and the vertical asymptotes, but we want to be mathematically correct in what we're saying. A vertical asymptote is a vertical line where a graph does not exist, and the description of a line is an equation such as x is equal to these numbers. So finding a vertical asymptote, you can focus on the denominator, what makes the denominator equal to 0, and so there we have our vertical asymptotes. Horizontal asymptotes, on the other hand, same idea in a way that they occur when we have a limit, but this time the limit is looking at approaching positive infinity or negative infinity. So what we're looking at is what's happening on the extreme right or left of a graph. And if it is approaching a particular value on either end, then that y value is the horizontal asymptote. And so this is the same example that I just did with the vertical asymptotes. So what we're going to do is take a look at how to find the horizontal asymptotes. So if I'm asked to find the limits to identify the horizontal asymptote, what I would need to do is find out what's happening on the positive end of our function. What we've done in the past with evaluating limits of a rational function like this is we've divided by the highest power in the denominator. So if I were to take every term and divide by the x squared, both in the denominator and the numerator, what we would see that we have in the top reduces down to 1 over x. The denominator is 1 plus 1 over x minus 2 over x squared. And what we learned earlier on with limits is that when you approach positive infinity with these fractions, 1 over a very large number is going to be 0. 1 is nothing to be evaluated, it doesn't have an x. And the other two terms are both going to approach 0 when we talk about x approaching positive infinity. So we would have plus 0, minus 0. So in the end, 0 over 1 is equal to 0. Now that's what's happening on the right-hand side as we are going to positive infinity for our x values. What's happening on the other end as we're approaching negative infinity. So the same idea as to what we would be doing, we would be reducing by dividing. So we would still see our original function dividing every term by the highest power in the denominator. So everything is divided by x squared. So initially this first step is identical. There's nothing different there. There's nothing different here. When I reduce each of these, now the only difference is when you take a look at approaching negative infinity, that this value is going to approach 0. It's just going to be on the negative side. And so whether you have negative 0.00001 or positive 0.00001 or some incredibly small number, it essentially is going to be 0. So in this particular example, it doesn't change much depending on whether you're approaching positive or negative infinity. And all of these values are going to essentially be zeros. So it's approaching 0 on both sides. And so what we end up having here is we have a horizontal asymptote at y is equal to 0. So what that means for us basically at positive infinity, at negative infinity, we have a horizontal asymptote. Our graph is approaching y equals 0 at this end, and it's approaching 0 at this end. And so I guess it's probably safe to assume that that whole y equals 0 is going to be our horizontal asymptote. So a limit process involves, remembering different methods of taking and finding a limit. So I'm going to do one more example here with finding the asymptotes, vertical and horizontal, of a radical function. So I'm going to start with the vertical asymptotes first because, again, those are the ones that are a little bit simpler. Vertical asymptotes, again, our denominator. What makes the denominator 0? X equals 2 is what would make the denominator 0, and so therefore that's where our vertical asymptote is. Horizontal asymptote, we need to find the limit as x approaches positive infinity of our function x squared plus 4 all over x minus 2. How we approached finding the limit of radical functions, we ended up taking out a common factor. In the bottom, if you take out an x from each term, you're left with 1 minus 2 over x. what we like in terms of limits approaching infinities, positive or negative, is whole numbers, like the 1. We like the fractions. Not so much this x, because it leaves things open to an unknown value, a concept in a really large number, not necessarily a numerical value. So in the top, with the radical, what we ended up doing earlier on is we took out an x squared. That was the largest common factor, so that first term was again a whole number 1. What we ended up having to do was to take now the square root of that x squared. And we can do this at this stage because the x squared is being multiplied to this factor. When terms are added or subtracted, you cannot simplify by taking the square root of anything. But once it has been factored, we have x squared times this bracket, then you can take the square root of the x squared. And if you remember a few absolute value properties from earlier on, when you take out the x squared from the square root, it is the absolute value of x. And so that's the only step that I did from here, took the square root. Now, because I'm approaching positive infinity, the absolute value of x has to be removed from the absolute values. You can't do anything with this x in the top and this x in the bottom until the absolute values signs are gone. So because I'm approaching positive infinity, that makes x a positive number. I can drop the absolute value and I do not need to make any changes to it. It already is positive. And so now that I have those x's both as a simple, just plain old x, now I can cancel them, top and bottom, meaning that I'm going to take the limit as x is approaching positive infinity of the square root of 1 plus 4 over x squared over 1 minus 2 over x. So now that I have done some simplification, on the top, when I think about x being positive infinity, we would have on the top the square root of that 1, which doesn't change, plus a 0 over 1 minus 0. Square root of 1 is 1 over 1 is 1. So as we're approaching positive infinity on the right hand of our side of our graph is approaching positive 1. We also have to take a look at what's happening on the negative side of our x-axis, the x values that are approaching negative infinity. And so when you take a look at a lot of what we are doing to this function, a lot of the steps are exactly the same. The only place where we're going to see a difference is down here. When we start talking about taking out the absolute value sign away from the x, the fact that we are approaching negative infinity now means that we're on the left-hand side where the values of x are negative, meaning that we have to replace the absolute value sign with negative x. The rest of the equation or the function at this time is the same. And I just skipped rewriting it exactly the same. But now that we're approaching negative infinity, when we cancel these x's, we have a negative that is left out the front of the radical. And so when we go to take the limit as x is approaching negative infinity, we're going to have a negative outside the front of a 1 plus essentially a 0 over 1 take away a 0. So in the end, we're going to have the square root of 1, which is 1, but a negative applied to that. So we'll have negative 1 on the top divided by positive 1. And so we have a limit of negative 1. So we have horizontal asymptotes. We have 2 of them at y is equal to 1 and y is equal to negative 1. In terms of a rough sketch of what's happening here, the best that I can explain, I guess, we have an asymptote at positive 1. we have an asymptote at -1. But what this is saying is on the right-hand side, at positive infinity, our graph is approaching +1. Whereas when we go from towards the left-hand side, negative infinity, our graph must be approaching the -1 asymptote. So I don't know if that's really what the graph looks like, but that's what the mathematical process is telling me. So the limit process is the official way of finding your horizontal asymptotes. It's not always easy to find the asymptotes of every function. Sometimes it does get a little bit involved. But that is how we would approach officially a horizontal asymptote. So just a couple of things that I want to mention before we're finished, because those are really the most important things that we need to know for Calculus 30, vertical asymptotes and a horizontal asymptote. But I wanted to make you aware of other kinds of asymptotes. For example, there's things called a slant asymptote. And this is a function that would produce a slant asymptote. Slant asymptote basically is this. Whatever the shape of our graph is, you can see that there is some kind of a linear function, a line, slanted, not vertical or horizontal. So we have something that has a slant to it. We can see a graph approaching on one end and another end here, but we have that invisible line of an asymptote. We can see that the graph is approaching. It is possible to have a quadratic asymptote where wherever your function is, you can see that there has an appearance of approaching a quadratic somewhere, that invisible asymptote. We're not required to know where or to identify quadratic asymptotes, but those are possible. Cubic asymptotes are possible as well. Again, we're not responsible for knowing or identifying or calculating or determining cubic, quadratic, or slant asymptotes. But there is a bit of a shortcut rule so that we can have an idea of whether we've got a horizontal asymptote, if there might be slant or quadratic or cubic asymptotes in there. We're not required again about a cubic asymptote, but what you're going to notice in a function, if you notice that the numerator degree is larger than the denominator degree by 3, that's what gives us a clue that we have a cubic asymptote. So difference of 3, cubic. For a quadratic asymptote, if our numerator degree, if we take that larger value minus the denominator degree, and then we have a difference of 2, we're going to have a quadratic asymptote. The slant asymptote is a little bit obvious with this function I have written down here. The numerator degree, take away the denominator degree, 2 take away 1 is 1, and so we have a slant asymptote there. So again, interesting to note that those may exist, but we're not required to know them. What we are required to know is about a horizontal asymptote. And if you have the numerator and the denominator degree being the same, then what you have is a horizontal asymptote. Now, how do we use this shortcut to find not only that there is a horizontal asymptote, but where is it? The asymptote is going to exist at the ratio of the leading coefficients. I'm just going to pop back here because we had back here a horizontal asymptote. This is not an example of where the degree was the same, so that doesn't apply. Let me flip over here. Here, where's the degree the same? Well, essentially, yes. The square root of an x squared means that we have a degree 1 overall, degree 1. So we have the same degree top and bottom, and the ratio of the leading coefficients. So when you take a look at the coefficients, the 1 and the 1, now this is the square root of 1, so we do have to think of it as both positive and negative. So when you think of a positive 1 and a negative 1 over 1, which is essentially what we ended up doing with our limit process, we ended up having those horizontal asymptotes at that ratio. So that's kind of a shortcut to finding your horizontal asymptotes. So what about those situations where your numerator degree is smaller. If you have a horizontal asymptote when you have a numerator degree that is less than the denominator degree. If that's the case where the numerator degree is smaller than the denominator, we do still have a horizontal asymptote, but it's on the x-axis at y is equal to 0. And again, sorry, I'm just going to flip back to what I just had there, because that's exactly what we ended up having way back with this example, where the numerator degree was smaller than the denominator. And so when you have the smaller numerator than denominator, that's when we have our horizontal asymptote at 0. So it's a shortcut. I'm always a little leery about shortcuts, but at least you have a formal process and a shortcut just to kind of clarify when you have some of those different kinds of asymptotes. And that's all we're doing with asymptotes today. Again, our focus is on vertical asymptotes and horizontal asymptotes for Calculus 30. Have a good day.